Welcome back to another video here at Hungry Turtle Code, and in this one we're going to be building collision detection and elastic collisions using pure JavaScript. Not a single library is used in the making of this video. So we're going to start off with a boilerplate that will be familiar with you if you followed along with my tutorial about creating snow with JavaScript canvas. So for those of you who haven't seen that, I'm just going to quickly run through the code that we have, but I'm not going to spend too long on it. If you don't understand, you can go back to those videos where I created snow in JavaScript and get more familiar with what I did there. So to start off, we have this canvas class. And we're just creating a new canvas, getting the context, putting it into the HTML, setting the width and height. And then we've got this setup where we're just creating some particles. Particles is another class that I'll show you in a second. And then we're just positioning it in a random place within the canvas. And then we have this update method where we're just resetting the canvas to blank every time, looping through all of the particles, updating their position, and then drawing them onto the screen. And then that is just running on every request animation frame, and that's how we're drawing stuff to the canvas. So now let's take a look at the particle class. So the particle class takes an X and a Y position, so we gave it a random one in that canvas class. Then it uses that X and Y to create a position vector. The velocity and acceleration vectors are just set to 0 initially. Each particle has a radius because they're just circles right now. And then in our update method, we update the position by adding on the velocity. We update the velocity by adding on the acceleration, and the acceleration we just set to 0 by multiplying it by 0. So all of these interactions are vector interactions which use our vector class. Then coming up to take a look at that vector class, so the vector class just takes an X and a Y, and then we have an add, a multiply, and a subtract method. So this is just vector addition, vector multiplication by a scalar, vector subtraction, and then a copy method that just creates an exact copy of the current vector using the current vector's X and Y coordinates. And then a static random function, so it just creates a vector in a random position within a given coordinate system. And that uses this random num_between function, which is just defined up here. And that just creates a random number between the two numbers that we give it. So that's what we've got, and that's what we're going to build on from here. And now before we move on, I'll just show you the HTML we have. So there's nothing special here. We're just importing our index.js as a script. And then we have one CSS style just declared in the head, which just sets the background of the canvas. So if we come back into our JavaScript, we can start creating something. So as always, I have a live server running in another terminal here. And that's just so that we can have live reloading of our code in the browser. Speaking of which, we can go into the browser and take a look at what we've got. So we just have two random particles within our canvas. If we refresh, they're in a brand new spot. And we keep refreshing, and we'll get two particles in a random spot every time. So in this video, we're going to try do collision detection. So of course, to have collisions, we're going to need some movement. So we'll just go into our particles and just give them a little bit of movement. So we'll just, instead of saying the velocity here is 0, 0, we'll just create a random vector using our static method. And this will be a random speed between, say, -1 and 1 and -1 and 1. Now if we come back into the browser and take a look, we have two particles that are just moving. But of course at this point, we have no collisions and we have no wraparound or anything like that. So as these particles approach the edge of the canvas, they're just going to disappear. And one's just approaching now, and we can see, bye-bye, it's gone, right? It's never coming back because it never changes direction, and so it's never going to loop back or anything, and it's just gone forever. And this one's about to disappear. So we want some basic collision detection around the edges, and that's the easiest collisions to deal with. And as soon as it hits the edge, which will be when the position plus the radius is at one of the edges, then we just want to reverse the velocity in the direction that it hit. So if it's moving up towards the top edge and it hits that, we want to just reverse the velocity in the upward direction to be in the downward direction so that it bounces off. So I'll come back into the terminal, and inside our particle class, I'll just create another method and I'll call it handle edges. And then into here, we'll be passed in the width and the height of the canvas. And we will just go back down into here. And then just after we call this update, we will also want to call handle edges and pass in this.canvas.width and this.canvas.height. So now that we're calling that, we can check if this.position.x is less than or equal to 0, or this.position.x is greater than or equal to width, then we want to reverse the velocity in the x direction. So this.velocity.x equals minus, if I could type, this velocity.x. Else if this.position.y is less than or equal to 0, or this.position.y is greater than or equal to height, then this.velocity.y equals negative this.velocity.y. So now hopefully, if we come back into the browser, when one of these particles hits, it's going to bounce, but it won't bounce quite right. So we do see that it kind of goes off the edge. And that's because we're not handling the radius as well. So we could just leave it like this and the bounce kind of works fine. But just for correctness sake, I'll also add in the radius. So back in our terminal, this will be this.position.x minus this.radius is less than or equal to 0, or this.position.x plus this.radius is greater than, and we will do the same here, plus this.radius, and this will be minus this.radius. Save, check back at what we've got, and there we have a much nicer bounce exactly on the edge. So that's a basic collision interaction with the edge. But that's not nearly as fun as other particles bouncing into each other. That's the real fun stuff. So we're going to want to detect when some of these particles intersect each other. So let's think about how we're going to go about figuring that out. So I'm going to do a basic sketch here to just kind of explain my thought process. So at any given point, we could have a particle here and another particle here. And that's within a total grid system where our vectors live, because the position of all of our particles is a vector. And fundamentally, a vector is just a line that points from the origin being this point over here, to the point in space where that position is. So that would be a vector that points from the origin up to here, and another one that points from the origin to here. So that's vectors. But now we want to decide, how do we know when these two particles have collided with each other? And the simple answer to that is if the distance between these two particles, we'll call that distance d, if d is less than the sum of the radii of each of these particles, then we've intersected. So let's explain that a little further. So we have a circle, or a particle, and that has some radius r. And then we can have another circle, or another particle, that has another radius r. They could be the same, they could be different, it doesn't matter. And at any given point in time, the distance between the center points of these two circles is some distance d. But of course, the distance from here to here, that distance there, that's just r. And same with this, that distance there is just r. So if we add r here and r here, the two radii of both of these particles, they are currently less than d. Clearly, we can see that. And that means they're not colliding. But if we were to draw this again in a configuration where these two particles have collided, like here, now we can have r here, and there's another r here, and d is the distance between the two center points. And because they're overlapping, d is clearly less than the sum of the two r's. And that's how we know that there's been a collision. when that distance between the two center points is less than the sum of the two radii. So now the question, how do we calculate the distance between the two vectors? So I'll erase all of this and we'll do another drawing. So in vector space, we can have a vector here. We'll call this A. And if we want to add another vector, we'll call this B. So if we want to add A plus B in vector space, all we do is take this point here, which is the start of B, and put it onto the tip of A, right here. So we draw that, very crude B, but that's basically B there. So we go from here up to the top of A, and then we draw B, starting from there up to there. And we end up in this spot here. And then if we draw a line from the origin where we started up to that new point, we now have a new vector C, and C is A plus B. And that's how vectors work. So you might say, that's all good, but how do I use that to calculate the distance between our two particles? Well, if we erase that and we think more about our problem, so we have a point here and a point here. Both of these are vectors down to the origin, which is here. And we want to calculate the distance in between these 2 points. So what we can actually do is subtract vector A away from vector B. And what is subtraction really? Subtraction is A plus negative B. And negative B in vector space is just B pointing in the other direction. So if we have a vector here pointing like that, the negative of this is the exact same line but pointing in the opposite direction. And we know how to do addition, so if we do A plus negative B, we'll end up with A here and then B pointing in this direction typically. So if we reverse that and start it from here, we end up with a vector that does this. So that's A plus negative B, and we end up at this point here, and then we draw a new vector starting from our original starting point to there. And by the law of parallel lines, this vector C is exactly the same as the distance between A and B. Just take a moment to let that sink in a little. We've just calculated the distance between A and B, which is the magnitude of this vector C, by taking away negative B from A. So if I erase all of this, so more formally, we can say the distance between any vector A and any vector B is A minus B, and then we take the magnitude of that new vector. And that's it. And we already know how to do A minus B because we've got that in our vector class. So the next question is, how do we calculate the magnitude of any given vector? So let's think about that. So we can have a vector A here, and that is something like this, and that's sitting on a grid. And this is maybe point 2, and this is point 3. So we want to calculate the length of this edge here. And we can do that using trigonometry, Pythagoras' theorem. So we've effectively got a triangle there and there, and we want to calculate this edge here. And if we call this A and this B and this C, Pythagoras says that A squared plus B squared equals C squared. And we want to calculate C, but we know A and B because that's the x and y coordinates of our vector. So if we know A and B, we can calculate C. C equals the square root of A squared plus B squared. A and B is the x and y of our vector, and x squared plus y squared, square root of all of that, is C, which is the magnitude of our vector. So with all of that, let's go back to our code and implement what we just discussed. So the first thing I'll do is just create a new method on our vector that calculates the magnitude. So we'll come down here and I'll create mag, and mag returns math.square root of math.pow this.x2 plus math.pow this.y2. So this is x squared plus y squared, and then the square root of all of that, and we are returning it. And while I'm here, I'm just going to refactor some stuff. So we have add, multiply, and subtract, but they're actually mutating the vector itself, and I kind of don't like that. I would rather have static methods that return a new vector than actually mutating things, because it's much easier to keep track of things when nothing gets mutated than if things are randomly getting mutated, and it can get quite buggy. So I'm just going to quickly go through here and turn all of these into static methods. It takes vector1, vector2, and that returns a new vector of vector1 plus dot x plus vector2.x and vector1.y plus vector2.y, and then we can delete that, and we'll do the same for the rest. And while I'm at it, I'll also create a static divide that just divides by a scalar. So we have that. So that just cleans up the cognitive overhead required because nothing is getting mutated. We're just using these static methods. So now to the actual collision detection. We'll write another method and I'll call it check collision, and we'll pass that another particle. So then we're going to want to find the vector that points from the current particle to the particle that we've just passed in. So that'll be const v equals vector dot subtract this dot position and particle dot position, and then we want the magnitude of that, which is the distance between the two, so const distance equals v dot mag. And now we can just console log out distance, and we're actually going to need to call this check collisions. So in our update function, we will just for let I equals 0, I is less than this dot particles dot length, I plus plus, current equals this dot particles I, and then we want to loop through the rest of the particles. So I'll create another thing, this dot particles dot slice I plus 1. And what we're doing there is, instead of looping through all of the other particles again, we only want to loop through the ones in front of the current particle we're looking at. So that's what this slice is doing. It's just slicing out another array, which is the current particle we're looking at, everything ahead of that. And then we'll loop through let p of rest, and then we'll call p.checkCollision with current. So hopefully, if I've done that right, probably haven't, we should be calling checkCollision, and it will be giving us the distance between the particle and the particle being checked. So if we come back into here, this .position.add is not a function, index 44. 44. This .position.add. Oh yes, so we updated this to use our new static methods, so of course we're going to need to do that. This .position equals vector.add this .position, this .velocity. This .velocity equals vector.add this .velocity with this .acceleration, and this .acceleration equals vector.multiply this .acceleration with 0. And we will try again. And there we go. So we're getting a stream of all of these figures, which are getting smaller and smaller as the two particles get closer together. which is exactly what we're looking for. So now, when this figure is less than the sum of the two radii of the particles, we have a collision. So let's do that now, where we can come into the check collision, and we can say, if dist is less than or equal to this.radius plus particle.radius, we will console log collision. And just to make this easier, I'm going to control one of the particles with the mouse. So I'll come down into the constructor, and I'll just say this.canvas.add event listener mouse move, and then I will say const mouse position equals new vector e.x, e.y, and then I'll grab hold of this dot particles 0 dot position equals mouse position. So here I'm just taking the first particle in our particles array and setting that position to the current position of the mouse. So now if I come back into the browser and I move my mouse around, I can see that I'm controlling one of the particles. Now if I put it right in front of here, we can see we're getting collisions when they're on top of each other, which is exactly what we hoped for. So I can come back and remove this mouse controlled thing because we don't need that anymore. We verified that our collisions work. So now we want to implement elastic collisions between our two particles. And this is kind of the complicated bit, I'm not gonna lie. So an elastic collision is a collision where two particles bounce off of each other and there's no kinetic energy lost. So they will bounce off each other perfectly. So in the real world, there's obviously sound created when things bounce off each other, there's heat, and there's kinetic energy converted into other things like sound and heat. But a perfect elastic collision is when there is no kinetic energy lost. They both perfectly bounce off each other. And that's what we're going to implement. I'm not going to go too deep into the maths, but I did find a paper that nicely illustrates a step-by-step process that helps us implement exactly what we're looking for. So I'll just pull that up. And it's called 2dcollisions.pdf. So I will zoom in so we can read it. And these are the steps. So basically, it's saying find the unit normal and unit tangent vectors. The unit normal vector is a vector which has magnitude of 1 and a direction that is normal, perpendicular to the surfaces of the objects at the point of the collision. So this is what we've actually already calculated. It's just not the unit normal, but we've calculated the normal vector, which is the vector that points from the center of one particle to the center of the other. But that vector currently has a magnitude equal to the distance between them. So we want to divide that magnitude by itself so that we reset the magnitude to 1. So let's do that. We'll just go through all of this step by step and hopefully it'll all start to make sense. So unit normal equals vector dot divide, and we want to divide v by the magnitude of v. So v is this, so that v is the normal vector between the two particles, and then if we divide that by the magnitude of v, we get a unit normal vector, which is exactly what we want. Of course, we could use dist here because the distance is v.mag and we're using v.mag here as well, so feel free to use the distance there. And then we want the unit tangent, which is the next thing. So this is just saying the unit vector of the normal, which we call unit normal, is done by dividing by the magnitude of the normal. So that's what we've just done. Next, we need the unit tangent vector. This is easy to find from the unit normal vector. Just make the x components of the unit tangent vector equal to the negative of the y component of the unit normal, and make the y component of the unit tangent equal to x components of the unit normal. I don't know about you, but that's kind of confusing. I find that difficult to hold in my head, but I think I get it. So, on our vector class, we will write another method and we'll call it getTangent. And that will return the tangent of the current vector. So return new vector. And then we want to set the x of the new vector to negative y. Just make the x component of the unit tangent equal to the negative of the y of the unit normal. So the x component of the tangent is negative y. So we'll say minus this dot y. And the y component is equal to the x component of the unit normal. So this is just this dot x. So that is our tangent. So now we can call that, and we'll say const unit tangent equals unit normal dot get tangent. So now we have our unit normal and our unit tangent. So what is the next step? Step 2, create the initial velocity vectors. We already have that because our particle class has velocity vector. So that's step done. Step 3, keep in mind that after the collisions... I feel like this is going to get complicated. Come on. Let's go. The tangential component of the velocities is unchanged, and the normal component of the velocities can be found using the one-dimensional collision formulas presented above. So we need to resolve the vectors v. Okay, moving on. Step 3. The values are found by projecting the velocity vectors onto the normal vector and the unit tangent vector, which is done by taking the dot product. So now we've calculated the unit normal and the unit tangent. But why do we need this stuff? And I think this is where I'm going to need to draw some more stuff. So let's start with a particle here. We'll call this A. And there's another particle that's just collided with A. And we'll call that B. So A is moving in this direction. And B is moving in this direction. So our normal line is the point from the center of A to the center of B. So that's our normal line. And our tangent line is a line that's there. So we've calculated the unit normal and unit tangent, which are the vectors that point in these directions with length of 1. But we need to figure out how much of the velocity of each of these particles is traveling along these two planes, the tangent and the normal planes. So B has force going in this direction. So that's the direction that B is traveling. So that's the force of B, and A's force is going this way. So we have those two forces. So if we just erase this and simplify a little, we have a grid where we've got the normal line and we've got the tangent line. So we'll just label this T and we'll label this N. So that's our normal and our tangent. And then we've got our vector B is here. So that's the force that B is exerting. And we've got a force of A, which is going in this direction. And that's A. So we can see here that B has a little bit of force in the T direction, because it is sticking out there. So some of this force, which is obviously going diagonally, some of it's going towards T, and some of it is going towards N. And the same is true of A. A has a little force going up towards the normal direction and a little bit going this way along the tangent direction. So we want to resolve the forces or the velocity of A and B along these axes. And the way that we do that is by taking the dot product of each of these with the unit normal and the unit tangent. So the dot product of B with the unit tangent will tell us how much force in B is exerted along the tangent line, and taking the dot product of B with the unit normal vector will give us how much force B is exerting along the normal line. The same is true of A. So if this is complicated to you or you don't understand some parts of it, I would highly recommend that you go out and check 3 Blue 1 Brown's video series on linear algebra, where he digs into what all of this stuff means and what dot products are and why it all works the way it does. Way better than I could ever explain it, so definitely check that out if you're interested. But staying with this video, we know that if we take the dot product of either vector A or B with the unit normal and unit tangent, we'll find out the components of those vectors in those directions. So let's implement the dot product method inside our vector class. So we will come up into our vector, and I'll write another called dot with a vector. And this doesn't have to be a static method because a dot product will always return a scalar value. So it's not actually manipulating the current vector. So we will return this.x times vector.x plus this.y times vector.y. And if my memory serves, that is the formula for the dot product. X components of one vector multiplied by the x components of the other plus the two y components multiplied. So I think that's it. So now using that dot product method, we want to calculate 4 values. And those 4 values, if we come back to our sketch, are the b component in the tangent direction, the b component in the normal direction, so that's 2 calculations, and then the a component in the tangent direction, and the a component in the normal direction. Those are the 4 calculations we want. So coming back into our code, let's implement those. So we come back into the collision detection. So just to simplify, we're going to want to know what a and b is. So we'll say const a equals this dot velocity, and const b is particle dot velocity. And then we want to figure out what the a normal component is, and that will be a dot unit normal. And then b in the normal direction will be b dot unit normal. And a in the tangent direction will be a dot unit tangent. And b in the tangent direction is b dot unit tangent. So now we've made those 4 calculations. So now let's check in our trusty PDF what the next step is. So this is the dot product stuff. So now step 4 is find the new tangential velocities after the collision. This is the simplest step of all. The tangential components of the velocities do not change after the collision because there is no force between the circles in the tangential direction during the collision. So the new tangential velocities are simply equal to the old ones. So I'm not sure this needs a drawing, but I'm going to do one anyway, just for the sake of completeness. So when we have 2 particles, A and B, that have just collided, the force of the collision is along the normal line. So the tangential line here doesn't have any force. The force is directed inwards by A and B. But there's no force along this tangent line. That's like fundamental. When 2 particles touch, there can't be any force along the tangent line. So if there's a particle coming this way, and there's another particle coming this way, and they collide at this point here, the force will be along this line where they've collided. But this particle here has a lot of energy in the upward direction. But this particle colliding with it will not change the velocity that it's moving upwards. It can't, because that's tangential to the actual collision itself. So all this is saying is the velocity of B after the collision in the upward direction will be exactly the same as the velocity of B in the upward direction before the collision. So now on to step 5, and here are the equations for step 5. So we want to implement those in our code. So we have the 4 components of A and B in the tangent and the normal direction. And as we've mentioned, the components in the tangential directions after the collision will be the same. So we don't need to do anything with A and BT. But we do need to do further work with AN and BN using these equations. We'll say const AN final equals, and that is AN times by, and then it's multiplied by mass here. We don't actually have a mass of our particles, but we do have a radius. So let's just assume the radius is the mass. So that will be this dot radius minus particle.radius plus 2 times particle.radius times bn, all divided by this dot radius plus particle dot radius, and then bn final equals bn times by particle dot radius minus this dot radius plus 2 times this dot radius times an divided by this dot radius plus particle dot radius. So that is those equations implemented there. Back to our PDF. Step 6 now. Convert the scalar normal and tangential velocities into vectors. This is easy. It's easy. Just listen. It's easy. Just multiply the unit normal vector by the scalar normal velocity. So the scalar normal velocity is what we've just calculated. These two calculations we've just done, they're the scalar normal velocities. So we want to take the normal scalar velocities we've just calculated, multiply those by the unit normals, and then take the tangential components that we calculated at the start and multiply those by the unit tangents. And that will give us the normal and tangential components of A and B after the collision. So const A and after equals vector dot mult unit normal, and we want to multiply that by an final, and const bn after equals vector dot mult unit normal bn final, and const at after equals vector dot mult, just move down, give us some more space, that is the unit tangent this time, multiplied by a in the tangent direction coming from up here, and b in tangent after vector dot mult unit tangent bt, and that is all of those components after the collision. And then find the final velocity vectors by adding the normal and tangential components for each object. So now we can say const a after equals vector dot add, and we want to add the normal after and the tangential after, and b after, same story, vector dot add b normal after and b tangential after, and those are the final velocities of our two particles. So we can say this dot velocity equals a after, and particle dot velocity equals b after. Now, I'm kind of scared. We haven't tested this code in a while. So, deep breath, to the browser, canvas fun. So we have no errors, so that's a good sign. So let's add a whole bunch more particles into our system. So let's add in a whole bunch more particles. So we'll say 100 particles, come back to the browser, and we kind of have some collisions happening. But what we'll notice, there's a bug here. So if you watch in the center here, we can see there are collisions happening. They're bouncing off each other. But there's situations like here where we kind of have a grouping of lots and lots of these particles, and they're not bouncing off each other, they're kind of attracted to each other. And the reason for that is that when we're putting particles onto the canvas initially, we're just putting them in a random place. So they could be overlapping when they're put onto the screen. So if they start overlapping quite a lot, maybe halfway, a collision's detected. when we first run the collision detection code. And they have velocities. Let's say, for ease of example, they're pointing in towards each other. So the collision detection will try and bounce them apart. So it will change their velocities to be in the opposite direction. They'll now be pointing outwards. And then the next cycle through the update will update their position according to that velocity. But if they were overlapping so much, they might move the position, but they're still overlapping. So there's another collision detected. In the next time the collision detection code runs, it will see that the velocities are pointing outwards and there was a collision. So it assumes that they've come from the opposite directions, but they haven't. They're actually trying to get apart, but the collision detection code will now reverse their velocities to point inwards, and that'll move them back together. And that has this effect of kind of like an oscillation attraction where they can't ever get apart from each other. And that's what you're seeing here. So there's somewhat of a solution that we can do here. And I'm just going to draw it because explaining it's going to be kind of tricky. So if we have two particles and they're quite a bit overlapped like this, we have a normal line which goes from the center here to the center here. So that's our normal line. And we can extrapolate that out. So what we can do is keep one of these particles fixed. We'll say we'll keep A fixed and we'll move B. What we want to do is move B along the normal line until it's exactly along the tangent. So then we move that out there, and then to get it along the tangent, we want to move that again until the distance between here and here is exactly equal to the sum of the radii, which is what we covered before. So we can do that when we detect a collision. We'll just take one of the particles and move it along the normal line so that it's exactly colliding along the tangent line. And then we won't ever get this weird overlapping thing. So then if we have a vector A and a vector B, and we want to move A along this normal line, along in this direction somehow, we can create a vector that points from A to B, and we can do that, we've done that several times, and then we can set the magnitude of this to the sum of the radii of these two particles, and then add that new vector, so that new vector where we've set the new magnitude to be the sum of the radii, we'll call that C, and then if we add the vector B and the vector C will point to the exact location that A needs to be to put it exactly tangent to our other particle. So that's what we'll do. Come back to our collision detection code. So what we have is a unit normal vector, and that is the vector pointing in the direction we want, and it's of unit length. So we can make that the length of the sum of the radii by multiplying it by the sum of the radii. Because, say for example, the unit vector is length 1, and if we want that to be length 10, we can just multiply that by 10. And if we want it to be length 13, we multiply 1 by 13. So if we say const correction equals vector.multiply unit normal by this dot radius plus particle.radius. And that is the new correction. And then we can create a new vector by adding together particle.position and correction. And then this dot position equals new v. And now if we come back into our code, we can see we don't have that weird interaction where there's the overlap anymore. Everything is spread out nicely. So initially, when we first dump all of the particles onto the canvas, they will be overlap, but the code we've just written will make sure that they're not overlapped anymore. And then the interactions will happen and we get nice collisions, just like we can see here. So at this point, all of our particles are uniformly sized, and as we're using radius as the mass of each of these particles, they also have the same mass. But we can tinker with the radius, and we'll start to see the effect of different massed particles. So here, radius, we can make that random num between, and we'll make it a random number between, say, 5 and 50, say. I don't know. And then come back. So you can see here that we have different mass particles, and the smaller ones with the smaller mass are getting thrown around really easily, and the big ones aren't being thrown around nearly as much. And that is the behavior we would expect. Larger mass needs more force to throw it around, and smaller mass is obviously much easier to throw around. So if you enjoyed this video, give me a thumbs up, hit the subscribe button, bell notification, all of that sort of stuff. If you really enjoy what I'm doing, I have a Patreon, so you can check that out and support the content that I'm creating. But until next time, stay hungry and keep coding.